Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O-Levels Physics. Today, we have set our hearts to solve a paper 4 of this subject. We call this paper ATP, Alternate to Practical. And for this purpose, we have selected May-June 2025 4-2 paper. This paper 4 belongs from the zone 2. So let's start today's paper. Okay, so May-June 2025 4-2 paper, alternative to practical. The time allowed is 1 hour and the total marks for this paper are 40. The question number 1 is showing up on your screen. He says a student investigates the refraction of a ray of light passing through a transparent block and determines the refractive index N of the block. The student's ray trace sheet is shown full size in the figure 1.1. The outline of the transparent block is shown by the rectangle ABCD. A line SR that meets side AD of the block is also marked. Okay. So here you have that sheet. Okay. So on that sheet, you see this is that glass block ABCD, and this is a line SR, which is touching the AD line at the AD face at the point R. Okay. So now what they say is on the figure 1.1, draw a normal to the block at the point R. Extend your normal 6 centimeter above the side AD and below the side BC. Okay. So what we have to do is that we have to draw a normal at the point R. Normal is a line which will be making 90-degree angle with the side AD. And then you have to prolong it. And so we have prolonged it 6 centimeter on the above the AD. And we also have prolonged it below the BC side. Okay. So this dotted line, you see this dotted line, this is the normal at the point R. Normal is making 90-degree angle with the surface. Okay. So then they say label the point where the normal crosses the BC of the block with the letter T. Measure the angle theta between the SR and the normal. So they say that when this normal intersect the BC side, you will name that point as T. So you can see here, I have written here T, and the angle between this normal and the SR, he says this angle is the angle of measure the angle theta between them. So we have to measure it. So you have to measure with the help of the protractor the angle between this normal and the SR. We have measured it, and it is approximately 30 degrees. So we have measured this angle, and this angle is 30 degree. Okay. So then they ask us to, the student positions in an illuminated slit on the ray trace sheet so that a ray of light passes along the line SR towards the R. Marks with small crosses X 2 points on the ray that leaves the side BC of the block. Remove the transparent block. On the figure 1.1, draw a straight line through the 2 crosses to meet the BC, side BC of the block. Label the point where the line meets the side BC with the letter E. Okay, so you can see here what we have done here. You see, along this, a ray has been sent, a ray of light. So the ray of the light entered into the glass, and from here, the ray of the light emerges from the glass. So when the light ray emerges on that ray, they have marked 2 crosses from where the ray was passing. So he asked us to join them with the straight line. So with the help of a pencil, what I have done, I have joined them until I cut the BC side, and this point has been labeled as E. You join this cross with this line with the help of a scale, and when it crosses the BC, I have labeled it as E. Okay. Then he says, okay, label the other end of this line as F. draw, okay. So the other end has been marked, this end of this line has been marked F. So this point where it cuts this line which you joined, you got this line by joining these two crosses. So this point is E and this other end is marked as F, okay. Then he says, label the other, okay. Draw a straight line from E to R. This shows the path of the ray of the light through the block. Okay, so what we have to do, we have to join this E point with the R point. And when you joined it, this is a continuous line. I have made a continuous line. This is the actual path of the ray inside the glass block. He asked us to join E point with the R. So this is the path of the light inside the glass block. So let me show you the whole thing. Okay, then he asked us to do another thing. He said, okay, measure the length of A of the ET. Okay, measure the length A of the line ET on the figure 1.1 ET. So he asked us to measure this distance ET. Okay, this point is T, this point is E. We have to measure it. When I measured it with the help of the scale, it was 2 centimeters. So you have to, with the help of the scale, measure this E and T, this length. Okay, the ET is 2 centimeters. Then he says, measure the length B of the ER on the figure 1.1. The ER, with the help of the scale, measure how much is this length. And he's calling it as B, small b. Okay. So we measured it and we have noted it down. Let me show you. Theta is 30 degree, the A is 2, and the ER is 6 centimeters. Okay. Then he said, on the figure 1.1, he said, on the figure 1.1, extend the line FE into the block until it meets the line RT. Label the point where the FE meets the RT at the letter with the letter G. Measure the length of the line EG on the figure. Okay. So what you have to do, you have to extend. Let me show you what they are saying. They are saying the line EF. Okay. So he said extend this line EF. So you can see this is E and F. This is E point, this F point, you extend this. So inside the glass block, I made it dotted line. So with the help of the scale, I extended EF until it cuts the RT line. When it cuts the RT line, I named that point as G. So let me show you. Let me make it bigger so you can see this. Okay. So what we did, we FE line, we extended it inside the glass block, this dotted line you see, and it cuts the RT line at the point G. So this point has been labeled as G. Then he asked us to measure what? He asked us to measure the line EG. He wants me to measure this side, EG, EG. With the help of the scale, measure how much is this EG. Okay. So I have measured it already, and that is something like, and he named it as C, and that is equals to the 4 centimeter. I measured it already. Okay. Now they are asking us, use your values from the C first part, C second part to calculate first value N1 for the refractive index of the block. So formula is given. So use the equation shown. N1 is equals to B by 2A. The B value is 6. The A value is 2. Just put those values and do the calculation. I have done that. This paper is actually has been solved by one of my students under our guidance, under my guidance. Okay. So her name is Fatma Anjam. We are thankful to her that she has written this paper. But and you know, this has been done under our guidance. We did it in the school. So N1 will be equals to B by 2A, that is 6, divided by 2 into 2, that is 4. So 6 divided by 4, that's 1.5. So the refractive index we think is 1.5. Okay. Then he says use your values from the C second part and the D To calculate a second value, N2, for the refractive index of the block, use the equation shown. This time the equation given is N2, refractive index number 2, that is equals to B by C. The value of the B is 6 and the value of the C is 4. And you know, when I calculated that, and this is 6 by 4, that's 1.5. So the N1 is also 1.5 and the N2 is also 1.5. Then they asked us, two quantities can be considered to be the same within the limit of experimental accuracy if their values are within 10% of each other. Compare your values N1 for the refractive index calculated in the E first part with the values N2 calculated in the E second part. State if your two values can be considered to be the same. Support your statement with the calculation. Okay. So you see the N1 value, the value which I just calculated, the N1 and one value is 1.5, N2 value is also 1.5. The N1 is exactly equals to N2. There is no difference in them. So they are considered to be the same because their values are equal to each other. Okay, then they asked us one source of inaccuracy in this experiment is careless measurement. Suggest other sources of inaccuracy in this experiment. For example, when you draw the position of the light ray which emerged from the block and you marked crosses there, you might you might use a pencil who is not sharp. And if your pencil is not sharp, then what will happen? You will draw a thick line, which might, the position of the ray might change due to the thickness of the pencil. The thickness of the light ray can lead to inaccuracy. You see, my student, make the thickness not of the light ray. Here, what you have to write, here you have to write the thickness of, so see, this sentence is wrong. I think that the thickness of your pencil, this word is wrong. So I think that here you have to write the thickness of the pencil can create inaccuracy. Okay, in your experiments. Okay, the thickness of the light ray, difficult in aligning incident ray with the SR, difficulty of placing crosses accurately. Okay, the marking scheme, she wrote the answer from the thickness of the light ray. If the thickness of the light ray is, it is thick, okay? If the light ray which you are using, if it's not thin, okay, then the position of the light ray can be misleading, because if the thickness, you see, from a ray box, the light is coming, and that ray box should be, the light should be like a beam. That beam should be very thin, okay? If your light ray coming from the ray box is thick, it's wide, so what will happen? To mark exact position, the student can go inaccurate because he might not put crosses in the middle. Another source of inaccuracy, I am saying that the source of inaccuracy can be your thick pencil. But this point is also very important, that if you see, if the thickness of the light ray means the light ray, the beam of the light which you are using, it is wide. If it is wide, then what will happen? The exact position of the crosses can be different, okay? The student might not put crosses in the center of that ray. He might put on one side, or he might put crosses on the other side, because the light ray is thick. So I also personally think that the pencil can also be a source of inaccuracy. Whenever we work on the experiments of the light, we always tell our students that the pencils must be very, very sharp. And you see, so this is the question number 1. This was of 10 marks. The last 1 mark, we have a little bit confusion. So let me show you the marking scheme, and you can pause the video and take your time with the marking scheme. Our answers are good. Okay, because of the photocopy, the answers might change a little bit whenever you measure some length. Okay, otherwise they are good. Okay. So the question number one is G part. I said that the answer should be sharp. He said that the thickness of the light can be misleading because you see, whenever we use a ray box, the beam should be very, very thin. So then you are able to exactly point the position of the accurately. You can mark the position of the light on the paper. If the ray of the light is thick, then it can be a problem because every student will can put crosses on different positions because the light ray is thick. So this is how you do the question number one. Let me show you once again the question number one. There we go. So this was that diagram which was given to us on which we were working. They have given you instructions and you only have to follow them. It's a very easy question. Okay, so now we are on the question number two, and let me see what the question. Okay, a student investigates the resistance of a thermistor at different temperatures. The student constructs the circuit shown. So here you have a battery, then you have a switch. Here you have a fixed resistor of 220 ohm. Here you have a thermistor whose resistance changes with the temperature. And here we have marked 3 points Z, Y, and X. So I have connected a voltmeter here across the thermistor, which will be telling you the voltage drop across the thermistor. And at point X and point Y, its wires have been connected. The voltmeter is connected parallel to the thermistor. The thermistor shown in the figure 2.1 is placed in an empty beaker and is at a room temperature. So this thermistor has been placed in a beaker, and in that beaker you can pour hot water to provide it a different temperature. But right now the beaker is empty, so the thermistor is subject to the room temperature. The student measures the room temperature R theta. The temperature is shown in the figure 2.2. So how much is this temperature? This is 20, this is 30. So this is, I think, 21. So this temperature, I think, is 21. So let me show you. So here we have noted that the room temperature is 21 degrees centigrade. Okay, then he asked us to, the student closes the switch, records the potential difference across the thermistor Vxy while the thermistor is at room temperature. You are in the top row of the table 2.1. Open the switch, the voltmeter is shown. So on this voltmeter, the reading now is how much? This is 3, this is 4. So this is basically 3.1. The reading is 3.1. Record the potential difference Vxy while the thermistor is at the room temperature in the table. So here you have to note down that reading. So that reading is, I think, 3.1. So in that table, we have to note down that reading. So that reading I will put here. That reading is 3.1. Okay. Then he asked us, the student disconnects the voltmeter from the point X and Y, reconnects the voltmeter across the 220 ohm resistor between the point Y and Z, closes the switch and records the potential difference across the 220 ohm resistor, and he's calling it VYZ. And while the thermistor is at the room temperature in the top row of the table 2.1, redraw the circuit shown in the figure 2.1 to on the page 5 to show how the voltmeter connected to measure the potential difference across the 220 ohm resistor. It's a 1-mark question. We have to draw this circuit diagram again. So what the student did, he removed this this voltmeter, which is connected parallel to the thermistor. He removed it from here and connected this at Y and Z, which will be parallel to the fixed resistor 220 ohm resistor, and it will tell you the voltage drop across that fixed resistor. He noted down how much is the voltage drop there. So then they asked us to draw the new circuit diagram in which the voltmeter has been connected parallel across the 220 ohm resistor. So you can see he removed it from here and he put that, so he put it here across the 220 ohm resistor. So it's a 1-mark question. So I hope you understand this. Okay, then he asked us, The student pours some hot water into the beaker containing the thermistor, places the thermometer into the hot water, and stirs the water gently. Wait for 30 seconds, measure the temperature of the hot water, and it is calling it the theta H. Measures new values for the potential difference Vxy and the Vyz while the thermistor is at the temperature of the hot water. The temperature of the hot water is 83 degrees centigrade. The student measurements are recorded in the table in the bottom row of the table 2.1. Explain why the student waits for 30 seconds before measuring the temperature of the hot water. You see, they have put the thermistor in that they have put that thermistor in a beaker, and now they have poured hot water in it. And so the temperature of the thermistor will change. The hot water is at 83 degrees centigrade, but he used a thermometer to measure the temperature of that hot water, which is in that beaker, which in which you have put the thermistor. And he waited 30 seconds before measuring the temperature on the thermometer. He put the thermometer and waits for 30 seconds. And whenever we are measuring the temperature of a hot body, we always wait. We put the thermometer in that hot liquid and then we wait 30 seconds. Why we do that? So that the thermometer can respond to that temperature. You see, when the thermometer will be put in, you will put that thermometer into a hot liquid, that the mercury of the thermometer will start rising, rising, rising. So then you are supposed to wait for like 20 seconds or 30 seconds so that the thermometer's mercury can reach to its highest level. So when the thermometer mercury starts rising further, so note that temperature, okay? So we do not do like this, that if you want to measure the hot temperature of a hot liquid, you put the thermometer into that liquid and immediately you note what is the reading on the thermometer. You give it some time so that the thermometer can respond to that temperature. The thermometer can show you the temperature of the liquid so that the mercury can reach to its highest level on that temperature. It's a 1 mark question. Let me see what she has written. My student, what she has written here. And you see, she has written the students waits for 30 seconds. So mercury can reach the maximum height to measure the highest temperature in that water. Okay, then they ask us another question. They say, explain why the student stirs the water before reading the temperature of the hot water from the thermometer. We always stir the water to make the temperature of that liquid uniform throughout the body of that liquid. So that's why we do the stirring. To ensure that the water is at uniform temperature, it means that throughout the body of the water, the temperature is same. Okay, that's why we stir it. Okay, then they say examine the table examine the data in the table 2.1. Compare the readings of the potential difference across the thermistor Vxy at room temperature with the reading for the potential difference across the Vxy at the temperature of the hot water. So that's what causes the difference in the reading. Okay, if you look at that table, I have done that table. Okay, so when you look at this table, when the thermistor is at the room temperature, the voltage drop is 3.1. And when the thermistor is at the temperature of the hot water, which was 83 degrees centigrade, the voltage drop across the thermistor is only 1.2 volt. You see, when the temperature has increased, the voltage drop across the thermistor has decreased. The reason is very simple. It's a negative temperature coefficient thermistor, which means that, and that is in our syllabus, that means that when the temperature of the thermistor increases, its resistance decreases. When the temperature of the thermistor increases, its resistance decreases. That's why the voltage drop across it has decreased. So this is their question. Let me see what the Fatma has written. The temperature of the hot water, resistance of thermistor decreases, due to which the potential difference decreases. You see, because of the temperature of the hot water, the temperature of the thermistor has increased. And when the temperature of the thermistor increases, its resistance decreases. That's why the potential drop across it has decreased. When it was at the room temperature, the potential drop was higher. and when it was at hot water's temperature 83 degrees centigrade, the potential drop across it decreases. So let's do the next one. He says the E part is the current I in the circuit is calculated using the equation I is equal to V YZ divided by the R, where R is the 220 ohm. Use the measurements recorded in table 2.1 to calculate the current at the room temperature and QR and the temperature of the hot water. So I can calculate the value of the I. Let me show you the table. So the value of the I is very simple. You see, this is the voltage drop across the that fixed resistor. When it is at the room temperature, the voltage drop is 1.4 and its resistance is 220. So when you divide 1.4 with the 220, you get the current flowing through it. And when it's at the hot water's temperature, which was 83 degree, the voltage drop across the 220 ohm fixed resistor is only 3.3 is 3.3 volt. So you can calculate how much is the current flowing through it, and the formula is the voltage divided by the resistance. So when I did calculation, its resistance is 220. So 3.3 divided by 220, that is 1.5 expo minus 2 ampere. So let me show you here. We have shown these readings. Okay, so this is that question. You see, at the room temperature, 1.4 ohm is the voltage drop across the fixed resistor, and its resistance is 220. So when you divide 1.4 with the 220, you get 6.36 expo minus 3. And or you can say 7 expo if we cannot round it off. Okay, so it's 6.36. Okay, so when at the hot temperature, it will be V YZ divided by the R 3.3 divided by the 220, and that is 1.5 expo minus 2. And you will note down these values in that table. Okay, so this is that table. Where is that table? So we have noted down those. I hope you understand those calculations. Very simple, straightforward. They just you have to understand the instruction, and then you have to do this. Okay. The F part is he says the resistance RT of the thermistor is calculated by the equation. This is also the voltage drop across the thermistor divided by the I. Use the data in the table 2.1 on the page 6 to calculate the resistance at the room temperature QR at the temperature of the hot water. Okay. So you see here you calculated the current because the thermistor and that fixed resistor, they both were connected in series with each other. The thermistor and that 220 ohm resistor, they were connected in series with each other. So the same current is flowing through them. So the current flowing through the fixed resistor is the same current flowing through the thermistor. So when at the room temperature, the thermistor, I know the voltage drop of the thermistor, and when it is flowing through the, you see at the room temperature, the voltage drop across the thermistor is 3.1 volt, and the current is 6.36 expo minus 3 ampere. And at the hot temperature, the voltage drop is 1.2, and the current flowing through the thermistor is 1.5 expo minus 2. So I can use these values and I can calculate the resistance of the thermistor when the temperature is room temperature, and the resistance of the thermistor when the temperature is higher, hot water's temperature. Okay, so I can show you that calculation. We have done that. Okay. So this is that calculation. You can see at the room temperature, the 3.1 divided by the 6.36 expo minus 3, that is 487.4 ohm. And at the hot water temperature, the resistance of the thermistor will be 1.2 volt divided by 1.1 expo minus 2 ampere, and that is 80 ohm. So this is how you got those resistances for the thermistor. He says that calculate the alpha, the average change in the resistance of the thermistor per degree Celsius for the thermistor as the temperature of the thermistor rises from room temperature to the temperature of the hot water. Use this equation, change in the resistance of the thermistor divided by the change in the temperature. Give your answer to two significant figures. So very simple. Okay, so you have to do Change in the resistance. The resistance changed from 487.4 and it went to 80, and the temperature changed from 21 to 83. So it's the you should have written like so it's 407.4 divided by the change in the temperature, that is 83 minus 21, and that is 62. So 407.4 divided by the 62, that is 6.57, which is 6.6. So that is the ohms per degree centigrade. 6.6 ohms per degree. This is the change in the resistance divided by the change in the temperature, and we got 6.6. So this was the question number 2. I hope you understand this. So let me show you the marking scheme of the question number 2. So my dear students, the question number 2's marking scheme is showing up on your screen. And because we have already done this, so if you want more time with this marking scheme, you can pause the video. I hope you understand this idea. Okay. So now we are going to the next question, which is the question number 3. And it is coming on the page number 10. Here we have. He says that a student investigates the stretching of a spring. The student suspends the spring from the clamp of a retort stand as shown in the figure 3.1. The student takes readings from the meter rule to determine the length of the spring. On the So here we have a retort stand, here we have a clamp, here we have a spring hanging here, here we have a vertical scale held with the help of a retort stand and a clamp. So on the student takes readings from the meter rule to determine the length of the spring. On the figure 3.2, takes readings from the meter rule level from with the top of the spring and the level with the bottom of the spring. Do not include the loops at the top and the bottom of the spring in your measurement. Record your readings to the nearest 1 centimeter. Okay, so here they have given, they say do not include these loops. Okay, so we will go from here and from till here. Okay, so the loops are not included, and you have to give the readings nearer to 0.1 centimeter. So reading level with the top of the spring and the reading level with the bottom of the string, it is something like 39 something, okay? And this is, I think, 42, I think something. So let me see what Fatma has noted. And here we go. So Fatma noted that is 39, the top is at 39, and the bottom is at 41.1. Okay, 39 and 41.1. Then the question is, he says, draw on the figure 3.2 to show how the student uses a set square to take a reading from the meter rule level with the bottom of the spring. Okay, you see the set squares, the two triangles which are present in your geometry box, those are called set squares. And the set squares can be used like this. Okay, so if you place the set square like this, you will be able to tell exactly what is the this top level and what is the reading on the meter rule. And using the set square like this, you will be able to tell what is the exact reading of the lower level of that spring. Okay, so this is how you will use those set square, and you have to draw this on the, we are done with that. Okay, then we have the B part. He says calculate the length L of the coiled part of the spring. Use the equation shown. L is equal to the reading level with bottom of the spring minus the reading level with the top of the spring. We know those levels, and we can subtract 41.1 minus 39. So that will be something like 2.1 centimeters. So the length of the spring is 2.9 centimeters. This is the question number 3. Okay, so it's like it's not 2.1, yeah. Okay, then they ask us to record the value of the length of the spring in the table 3.1 on the page number 12 for a load of 0.0 Newton. So when there is no load on the spring, this is the length of the spring, which is 2.1 centimeter. The student places a load L of 1 Newton on the spring, takes readings to determine the new length L of the spring. So he put some load and note down what is now the new reading. He call it small L. The top of the spring does not move, but the bottom of the spring moves downward. The student determines the new reading on the rule level with the bottom of the spring is 45.2 centimeter. Calculate the new length L of the spring. So the top is still there, but the bottom has gone down when you hung a 1 Newton load with with that spring. Calculate the new length of the spring, okay, and record your answer for the new length L, small L, for a load L if 1 Newton in the table 3.1 on the page number 12. So here we have that, okay. So when the load is 0, what is the reading? What is the length of the spring? When the load is 1 Newton, what is the length of the spring? We have done that. You see, uh, so the length of the spring when the load is 1 Newton will be 45.2 minus 39. That will be 6.2 centimeter. And then I will put that value in this table. So when the load is 0, the length of the spring is 2.1. We call it unstretched length. This is L naught, or you can say capital L. And when the load is 1 Newton, the length is 6.2 centimeters. We call it L, or stretched length. On the grid provided in the table 3.3 on the page 13, plot a graph of L on the y-axis against the load on the x-axis. Start with the origin 0, 0, draw a straight line of the best fit. That's a 4 marks question. You see, 0 at 0, the length is 2.1. At 1, the length is 6.2. When the load is 2 Newton, the length is 10. When the load is 3 Newton, the length is 14. When the load is 4 Newton, the length is 18.2. When the load is 5 Newtons, the length of the spring is 21.9. Okay, so we have to plot it on a graph paper. So let me show you. So you can see here. Here you can see we have drawn that graph. So on the x-axis, I have taken load, capital L, its unit is Newton. Every 2 centimeter represents 1 Newton. So 1 Newton, 2 Newton, 3 Newton, 4 Newton, 5 Newton. And on my y-axis, I have represented the length of the spring. So in centimeters, so the length of the spring, 2 centimeter representing 5. So here we have 5, 10, 15, 20, 30, and 20, 25, and 30. So label this. We have labeled it. You can see here, the Fatma has labeled it as small l, the length of the spring in centimeters. And on the x-axis, she has labeled load, capital L, and the units are Newton. So then she plotted those points. Those points have been plotted here. Which points? I can show you. So we plotted these points. 0, 2.1 is 1 point, 1, 6.2, then 2, 10, then 3, 14, then 4, 18, then 5, 21.9. So they plotted those points here. Then they joined them with the line of the best fit, and you can see this is the line of the best fit. It's a 4-mark question. I hope you understand. Then he says use the data in the table 2.3.1 and the graph in the figure 3.3 to determine the extension of the spring when the load of 3.5 Newton is added to the spring. Show your working. Okay. So when a load of 3.5 is added, so from here, I will go to the graph and at this 3.5 Newton load, and I will check what is the length. Okay. So the length is 15, 16, something. Okay. Now I know the length when the load is 3.5 Newton. Where is that? Okay. When the load is 3.5 Newton, the length of the spring is 16 centimeter. So how much is the extension? Extension is the stretched length minus the unstretched length. So that will be 16 minus 2.1, that will be 13.9 centimeter. So the extension at the 3.5 Newton load is 13.9 Newton. That is length minus the unstretched length. Okay. Then he says that the student suggests that the stretched length L of the spring is proportional to the load L. State if the data in the table 3.1 supports that suggestion. Justify your statement using the data in the table 3.1 on the or the graph in the figure 3.3. Statement, you see if the length of the spring is directly proportional to the load, then what will happen? The graph will be a straight line, and the graph will have positive gradient, and it will pass through the origin. Okay, so let me. So you see, a student suggests that the stretch length L is proportional to L. If the two quantities are directly proportional to each other, their graph is a straight line. It has a positive gradient and it passes through the origin. If you look at this graph, okay. So look at this graph. Where is that graph? Let me go to that graph. So here you have that graph. Look at this graph carefully. It has positive gradient. It's a straight line, but it is not passing through the origin. It is not passing through the origin. Okay. So from here, I can say that these two quantities are not directly proportional to each other. Another very important thing from the table I can show you. You see here, you double the load. If the two things are proportional to each other, directly proportional to each other, if you will double one quantity, the other quantity will also double. Okay. So it's here, the load is 1 Newton, you made the load 2 Newton. So you double the load. But the length has not become double. The length has increased, but it has not exactly became double. So for example, here you see your load is 2 Newton. You made the load 4 Newton. Okay, so you double the load. The length has not doubled. The double of the 10 is 20. It is only 18.2. So this is the reason why he's wrong, because you see the when you double the load, the length of the spring do not doubles. That means that they are not directly proportional. No, it is not directly proportional. If we double length, then the load should also be you should write like this. You should not write like this. If we double length, then the load should also be double. No, right? If we double load, then the length should also be double, because we are changing the load. The length is the change in the length is a consequence. Okay. So if we double the load, then the length should also be doubled. If doubling the load does not double the length, if doubling the load does not double the length, as it is in the figure 3.3, then they are in that table, then, or you can say graph, then they are not directly proportional. Okay, so another thing you can say that the graph is a straight line, but it is not passing through the origin. Okay, a line of, I hope you understand this this 1 mark question, and the Fatma has changed these words. If we double load, then the length, this word should be length should also be doubled. Okay, so I hope E part is clear to you. Then he says the line of sight. Parallax error can be occur when readings are taken from the meter rule. State one practical technique other than using a set square that ensures accurate readings are taken from a meter rule. You see, your line of sight must be perpendicular to the scale from where you are taking the reading. Your line of sight must be perpendicular to the scale from where you are taking the reading. Keeping the eye perpendicular to the meter rule ensures the accurate reading. Okay. Okay. Then we have, he says, the student repeats the procedure described in the C part two more times and average the readings before calculating the spring length L for each load. Explain why the student does this. You see, whenever you repeat an experiment again and again, so by doing so, the random errors, they decrease. Okay. So when you take the average, your precision becomes more and more. You become closer to the accurate answer. It's possible that you come close to the accurate answer to get accurate results, and it prevents error in the final answer. Let me show you from the marking scheme. The marking scheme has used very excellent words, and let me decrease the size so you can see the whole thing. Okay. So reduce the effect of random errors improves the precision. Instead of saying accuracy, say precision is increased. You see, accuracy means to come near to the accurate answer. But when you are doing the experiment, your readings should meet with, let's say I do an experiment 3 times. So each time if my reading is in agreement with each other, 3 times readings, they are very close to each other. This is called precision. They might be precise, but they might not be accurate. For example, if I have a faulty instrument, so every time I'm taking a reading, I get the same reading again and again. That reading might not be accurate, but it is precise. Okay, precise means that every time you're taking a reading, it is very close to each other. Okay, so that's precision. So when you repeat experiment, your precision increases, the effect of the random errors decreases. So please use these words. Okay, Fatma have used a little different words. Okay, so let's. Okay, so we are done with the question number 3. So let me show you the marking scheme once again. You can see, you can pause this marking scheme and you can take your time and read it. So you see, I have used, instead of writing myself the paper, I have used one of the papers, the answers written by my student. And I was also, she was writing the answers in the supervision still, but you see, still you can make some, means some errors. So this is very important. Okay. So whenever you're writing, your teacher is telling you what to write, but even the teacher is telling, he is repeating again and again. The student might be changing the words a little bit. And by changing the words, what happens? Sometimes this is possible that the meaning of that sentence changes. Okay. So, but there's no problem. We are learning. And in the learning process, mistakes are good. We learn from them. Okay, question number 4. As a metal ball falls through a liquid, it experiences a frictional force from the liquid that opposes the motion of the metal ball. Plan an experiment to determine the relationship between the density of a liquid contained in a measuring cylinder and the average speed of a metal ball falling through the liquid from the surface of the liquid to the bottom of the cylinder. The average speed of the ball is calculated using the equation. Average speed is equal to the distance traveled by time taken. The arrangement of the apparatus is shown in the figure 4.1. So what is happening here? So they have this measuring cylinder, and in this measuring cylinder, they have put some liquid and they know its density. Okay. So what they did, they put a metal ball here, and when the metal ball starts sinking into this, they started a stopwatch, and when it will reach the bottom, and then they will stop the stopwatch. You can measure this length of this column, liquid column, in which that ball has traveled, and you can divide that distance with the time taken, which will be shown on your stopwatch, and you will get the speed. Okay. So the apparatus available are a measuring cylinder, a metal ball, a selection of different liquid whose densities are known. So we have different liquids. Each liquid has a different density, and the density is given to us. Some liquids will have less density, some liquids will have more density. And we will do this experiment. We will drop the ball here gently, and we will note down how much time it takes to go from the top to the bottom of this measuring cylinder. So our selection, I mean the liquid, okay? the densities of those liquids which we will be using, they are known. You may also use any other apparatus commonly found in a school laboratory. In your plan, include any other apparatus needed, a brief description of the method, including that you will measure and how you make sure that your measurements are accurate. The variables you will control a result table to record your measurements. You are not required to enter any readings in the table. How you will process your results to draw a conclusion. Okay, so we are basically looking for the relationship between the speed of the metal ball in that liquid, and it's falling down. That ball is falling down in that liquid, and the density of the liquid. Okay, so the experiment is very simple. What I need a stopwatch, I need a tape measure or a ruler to measure what is this length of the liquid column. So I will drop my ball here. I will start my stopwatch, and when the ball will reach at the bottom of this cylinder, I will stop my stopwatch. Okay. So, and the density of this liquid is already known to me. So I will divide this distance with the time taken, and that will give me the speed of that ball. Then what I will do, I will use another liquid whose density will be different. But I will make sure that the liquid, the volume of the liquid is same. I will make sure that this length of that liquid is same as in our first procedure, first experiment. So then I will drop the ball and I will repeat the procedure. I will note down the time. I will calculate how much is the speed of the ball in that second liquid is. Okay, then I will do it with the third liquid. Okay, now you need a stopwatch, you need measurings, you need meter rule or a measuring tape. The things which should be kept constant. You see, the things which should be kept constant are the volume of the liquid. Each time you take a liquid, its volume should be same, which means the length the ball has to uh, from here to here. That length will should be same. The volume of the liquid every time should be same. The ball, its mass, its shape, its material should be the same. The other environmental conditions like the temperature and the wind in your lab should be the same. Okay. Then the table you will draw and make 3 columns, for example, I think. Note down what is the density of that liquid, then note down how much the time the ball has taken to go from the top of that oil to the bottom of the liquid, and then another column for the speed. Okay, and when you draw this table, you will also have to note down their units. Okay, for example, the density can be kg per meter cube, the time can be seconds, and the speed will be meter per second. Okay, then at the end, what you will do, you will draw a graph, and on the x-axis you should represent the density of the liquid, and on the y-axis you should represent the speed of the ball in that liquid, and you should plot those points, and then by looking at the shape of that graph you will be able to tell what is the relationship between the speed of the ball in that liquid and the density of the liquid. So let's see what Fatma has written, and I hope I have tried to explain to you that what you should write. You see, I always tell my students that you always can write a better answer than the answers my students are writing or I am writing. So the we just give you the idea that what you should write. You should consult the marking scheme. You should consult the ideas which we are giving, and then you should write. For example, the table which you have to draw: density, time, and speed. The density unit, the mentioning of the units is very important here. Kg per meter cube, or you can say gram per centimeter cube. The time the ball takes to go from the top of the oil or liquid to the bottom of the oil or liquid, you can say the time is in seconds. The speed will be in the meter per second. The graph which you have to draw for the conclusion, on the x-axis, you will represent the density, whose units will be kg per meter cube, or they can be grams per centimeter cube. And on the y-axis, we will represent the speed, which will be in the meter per second. Okay, so let's read what she has written. You see, this is very important. This is a very good example what the student writes. At first, we will put a known liquid in measuring cylinder. A known liquid means I know its density and measure its height using the measuring tape. Okay. So in that measuring cylinder, whatever is the height of that liquid, you will measure it with the measuring tape. Then we will put the ball in the liquid and measure time it takes for ball to reach the bottom of the cylinder. So the point when it touches the top surface of the liquid, you start your stopwatch, and when that ball will reach the bottom of that liquid, you will stop your stopwatch. Okay, we will repeat this process for different liquids whose densities are known. She has not mentioned that densities are known. The mass of the ball and the shape of the ball, along with the height of the liquid, every time is to be kept same. We will record times of all repetitions. We will record all the times and make a table including its values of the density, time, and in that table we have made three columns. The first column is of the density, then the column is of the time, the third column is of the speed. Speed we will calculate, okay? Speed is equals to the distance the ball has moved divided by the time taken. Would be calculated by the formula speed is distance divided by time. With the help of a table, we will plot a graph. So we are interested in the density of the liquid and the speed of the ball in that liquid. So we can plot a graph by taking, we will plot a graph with the density on the y-axis and the speed of the ball on the x-axis. You see here she made a mistake. The graph with the density should be on the x-axis. Here, he should write x-axis, okay? You see the student makes mistakes, okay? So the density is supposed to be represented on the x-axis and the speed of the ball. So let me it. So this is the word should be the x-axis, okay? The density should be represented on the x-axis, the speed of the ball on the, this should be represented on the y-axis. By the graph, we could figure out if the density and liquid affects the, if the density of the liquid affects the average speed of the ball. By looking at the shape of the graph, you can see what is the relationship between the speed of the ball and the, you see, we have used a paper written by one of my students, and I just wanted to show you that although you have a very clear understanding that what is happening, but still you can make some mistakes. These mistakes are very, very important to understand. You see, let me show you the marking scheme. I always tell you don't follow what we have written. Consult your marking scheme. We are showing you the marking scheme. Consult that marking scheme and write a better answer. You can always write a better answer, sir. So I showed you how my student made some mistakes, and they are minor mistakes. We can correct them. And by making mistakes, you see, it's very, very important that we learn. My students learn. They get polished when they make mistakes, and we correct them. So the marking scheme for the question number 4, which is a planning question, is in front of you. It's a 6 marks question, very, very important. I hope you understand, and now you can write this. And this is the graph my student wrote, and this is what he wrote. And let me increase the size so you can look at an answer, her answer, and then you can write your own. Okay, so you can pause the video and you can take your time with this paper. So then we have reached the end of this paper. So my dear students, we have completed this paper, and you know this paper is this paper was May June 2025 Cambridge O Levels Physics 505442 paper. In this video, I have tried to present you and describe to you the solution of this paper to the best of my knowledge and my abilities. You can always write a better answer, but it's just a guidance, okay? So how to write these things. You should always consider the look at the marking scheme, okay? So the one very important thing is that the paper and the marking scheme which I used in this video, they are the property of the CAIE, and I only presented you the solution. So I hope that this video will be helpful to you, and this will provide you guidance, and it will make your answers better and better. So thank you very much. Please like this video. Please share the link of this video with your friends, with your class fellows, with your junior students, with your teachers. You see, when you do this, you provide support to my work, you provide appreciation to my work. Your support and your appreciation is very, very important for me. So, sir, thank you very much. Have a good day. God bless you all.